So, this is an example of a modern radio receiver, right. So, this is the RF signal, and the RF signal has got signals modulated on both the sine, on the cosine and the sine carriers, right. And in other words, this makes the spectrum asymmetric about what frequency? About f naught, right. And the idea behind this is to be able to efficiently use spectrum. Now, you have the antenna and some a little bit of amplification. Then as soon as possible, you multiply the signal with what is called a local oscillator, which generates f naught, all right, which is the center frequency. Okay. The moment you multiply this by cos and sine, and these are low pass filters. So, what comment can you make about the signal that you get here? Which of these baseband signals do you get there? Mi, okay, that is supposed to be I actually, but never mind, right. Okay. And then you have some more gain and some more filtering if necessary, and so basically at the end of the baseband chain you basically get some gain times Mi. Remember that the RF signal is still got desired signal and a whole bunch of interferers, right. Where are the interferers getting knocked off here? What is happening? So what is happening to the spectrum? The moment you multiply it by a cosine, what happens to the spectrum? The desired, the whole RF spectrum shifts to this whole thing is moved to 0, and another one is moved to 2f naught. The 2f naught anyway gets is gone because of the high frequency attenuation of this low pass filter. But even so, if you make the low pass filter have only a bandwidth of the desired signal, namely B, then all the interferers are basically eliminated by low pass filters rather than band pass filters, correct. And do you think it is easier to make a low pass filter or a band pass filter? Is it easier to make a sharp low pass filter or a sharp band pass filter? You have seen this in fact in one of your assignments, right. Basically, as the frequency of the band pass filter becomes higher, if you want to receive a signal bandwidth, a certain signal bandwidth at a much higher frequency, you have a double whammy. Not only is the center frequency higher, so any band pass filter you make becomes more difficult to do. The Q also becomes higher because center frequency is higher, bandwidth remains the same, so Q is higher. So making something very high Q is reliably is very difficult. So it's much easier to filter using low pass filters, and now these low pass filters, as you've already seen in this course, can be realized very efficiently without the use of inductors by using op amps R and C, all right. So basically this is the baseband change. So most of the gain and filtering is obtained at baseband. Now at low frequencies, the isolation you can get between nodes is much higher than the isolation you can get at RF. So the fact that you have a lot of gain at baseband is no longer problematic, because the isolation you can get is several orders of magnitude higher, right, and therefore feedback is not a problem. All right, okay, and filtering happens at baseband. So no bulky inductors. All right. Now, what else? What comment can we make about the center frequency? Earlier, remember in the tuned RF receiver, we had to tune the center frequency of each one of those band pass filters separately and make sure that they're all kind of exactly the same. Here what determines the center frequency of the effective bandpass filter that you see from here? It's the center frequency of the oscillator frequency, right? And it turns out that you can make the oscillator frequency very, very precise by using phase lock techniques, right? So, the center frequency basically there's no need for ganging of multiple stages, all right. What determines and remember one more problem with the tuned RF receiver was when we changed the center frequency, the bandwidth of the band pass filter would change because Q remains the same, omega naught changes, correct. Here what determines the effective bandwidth of the band pass filter that we see? It's the bandwidth of the low pass filter which is responsible for selecting the channel that you want, right. So, the channel bandwidth is decoupled from the center frequency, correct. And the next thing is, hey, what happens if, I mean, you are right, there is no, feedback in the baseband chain is not a problem. What about feedback from here to here? Well, this is a baseband signal, right. So, even if some of it couples to the antenna, this is basically, this will go through and get down converted. So, if this is baseband, once you multiply it up by cos, what happens? It goes to f naught, and then the low pass filter will go and kill it completely, right. So, effectively because the baseband signal and RF signal are widely separated in frequency, the feedback loop is essentially broken, all right. So, there is no spurious feedback, all right, which can kill us, right, because most of the gain and selectivity is obtained at baseband, where isolation is fundamentally much higher, all right. The center frequency of the effective band pass filter that you are making is set by the frequency of an oscillator. It can be changed to whatever value you want without having to bother about, oh well, I have 10 band pass filter stages, so how do I make sure that all those center frequencies are the same? And there is therefore all the problems associated with mechanical tolerances of components, etc., is all gone, correct. The selectivity is obtained at baseband, right, and it's much easier to make a sharp low pass filter than it is to make a sharp high frequency band pass filter. And the channel bandwidth is decoupled from, correct. So, what is the key to the operation of the modern radio? What is the difference between what the tuned RF receiver and this receiver? The tuned RF receiver from the antenna to the final detector was a linear time invariant system. What comment can we make about the system from here to here? Well, if you kind of look at one of these chains, you can see that you have the RF signal here, then we have some kind of multiplier where it gets multiplied by some A cos say 2 pi f naught t. Then there is a lot of gain and filtering. I am going to represent that by a single block diagram. I will call that so I will call that H of S, which is, this is a linear time invariant system, and this is the output. Okay, this is low pass and gain. So, what kind of system is this? Is this linear? Well, even though you see the multiplier and you might first be tempted to think that it is nonlinear, right. Remember that linearity just simply means that if you put in x1 and you get y1 and you put in x2 and you get y2, when you put in alpha x1 plus beta x2, you should get alpha y1 plus beta y2, right. That is clearly satisfied in the case of a multiplier. So, this is linear for sure. What comment can we make about time invariance? What is, let us remind ourselves what time invariance means. So, if you put x of t, let us say you get y of t. If you put in an input x of t minus t1, you must get y of t minus t1, and then this is what do you call a time invariant system. And please note that time invariance has got nothing to do with linearity. These are two fundamentally different things. Now, is this system time invariant or time varying? Time varying, because if you put in x of t and you look at the signal here at the output of the multiplier, you basically get x of t a times x of t times cos 2 pi f naught t. If you put x of t minus t1, then you get a times x of t minus t1 times cos 2 pi f naught t, right. And clearly this is if you delay this by t1, you do not get that. So, this is multiplication is a linear but time varying operation. So, as you can see, the key point that makes the modern radio receiver work is there is a fundamental difference between the tuned RF receiver and the modern radio receiver. And if you kind of want to think of one key feature that makes it work, it is the exploiting of time variance. Okay. So, these were called, so this whole multiplying by the local oscillator was this was called heterodyning, right. And this is not the only way you can make a radio exploiting time invariance. There is no reason, for instance, to go all the way to baseband. You can go to what is called an intermediate frequency, and from the intermediate frequency you can go to baseband. Each one has got its own trade-offs, but if you open up your cell phone today, you have two wireless LAN receivers, two Bluetooth receivers, multiple cellular band receivers, and so on, and all of them are pretty much based on this architecture, this radio architecture, which is called the direct conversion architecture, right. Right. This part is what you call, I would call it more technology enabled, in the sense that, well, 100 years ago making A to D converters and DSPs was not possible. Now it is, and therefore you exploit that to use more and more complicated exotic signal processing algorithms to make sure that you are as spectrally efficient as possible, so that the telecom companies can make money. All right, excellent. So, the moral of this entire story is that the key to making the modern radio receiver work is time variance. Now, that apart, if you look at any electronic system today, so this is the block diagram of any modern electronic system. You know that most of the information is eventually stored and processed digitally, but the real world signals that you were interested in, namely, I don't know, maybe audio, maybe radio, whatever, they are all in analog form, and so these signals are all what you call signals that are continuous both in time and amplitude. and the DSP only understands signals at discrete instants in time and discrete amplitude levels. So, you need basically some electronics or some way to interface between the real world and the virtual world. Does that make sense, right? And what enables you to do that? I mean, how can you take a signal that is continuous in time and represent it losslessly as a sequence? Pardon? Yeah, sampling, the Shannon theorem basically is telling you that if the signal is varying sufficiently slowly, you don't need to keep looking at the signal all the time. You only look at it once in a while and then you're good enough, right? And to prevent aliasing, you need an anti-alias filter. So, this is you have a sensor. The sensor signals are typically very small, so you need to gain them up a little bit, right? And then you need to have an anti-alias filter. We already have seen what the features of this need to be. Then you sample and quantize, right? So, quantization of course is a process where you lose information, but if you make this the quantization step sufficiently small, then it stands to reason that the loss of information is so little that for all practical purposes you can ignore quantization. So, the A to D converter for all within quote signal processing purposes is simply is equivalent to a sampler, right, which takes a continuous time input and gives you the discrete time. In other words, you have a continuous time input, and then in the Oppenheim and Schaefer book, you basically say, oh, well, this is my discrete time out, right. So, the A to D converter is basically taking this continuous time in and giving you the discrete time out, all right. And if you look at what A to D conversion does, it is also, what is sampling? I don't know why the resolution is so poor, but okay. So, as you can see here, this is what the A to D converter does, but in mathematically what's happening? You're sampling, right. So, sampling in the continuous time domain is in principle taking x of t and multiplying it by an impulse train, where these deltas are continuous time Dirac impulses, right. So, you now get xs of t, which is something like that, okay. Then you have some contraption, in a signal processing model we do not worry about what that contraption is. We convert these continuous time Dirac impulses into discrete time Dirac impulses, where the each discrete time impulse is basically corresponds to the area of that continuous time Dirac pulse. And then once you get that, you quantize it to the nearest level, right, and therefore, there is some quantization error, okay. And we get the quantizing, correct. And as I was saying, in your application, you want to make sure that this Q of n is sufficiently small, so that for all practical purposes, as far as the system is concerned, you can think of it as being 0. So, that is the job of the A to D converter designer, we do not have to worry about it. So, again, as you can see, is sampling a time invariant operation or a time varying operation? It is a time varying operation, because again you can see that you are multiplying it not with the sinusoid now, but with a periodic train of impulses, right. So, therefore, to cut a long story short, whenever you pick up a phone to do anything, you are pretty much harnessing the power of time variance, okay. And likewise, whenever you build an electronic system with an A to D converter in it, which basically today is all systems, you are also, the key systems aspect of all these systems is that we are exploiting time variance to do whatever we are supposed to, okay. So, So, the bottom line therefore is that time varying systems are everywhere, right. So, the question is not why should we study time varying systems. The question is how come we did not study, we never bothered to study these important class of systems ever, right. Okay. So, we spent, in your undergrad classes, you have probably spent, taking, you have taken signals and systems, you have taken linear circuits where you basically learn Laplace and Fourier and so on. And then you have taken analog circuits and, and you have taken, communication and so on, right. Where every time you are basically studying circuits that are and techniques that apply to systems that are linear and time invariant, whereas the application of time variance is, is everywhere, right. Okay. So, in the lectures to come, we will fill that shortcoming in your background. Does it make sense? Okay.